This is an introduction to the SCION model. What I'm going to show you here is the two most important code files, what each bit of the code does, and then how to do simple runs. So I'm working in MATLAB here. I've got the MATLAB terminal window open here, and I've got two of the SCION model code files open here. So I've got the equations file and I've got the initialize file. So the initialize script is the script that you run if you want to run the model, and the equations file contains a function which is then passed to the solver in order to solve the model. Typically, if you're making modifications to the model, you'll want to be modifying probably both of these scripts, but most of your modifications will probably end up in the equations file. So I'll just start here running through kind of line by line, describing what is actually done here. So first, when you begin the initialize file, this itself is defined as a function. This is so you can run it a bunch of times for a sensitivity analysis. You clear the old outputs, you set up some global structures, which we're going to use to store our data. You then check whether we're running this by running the initialize file or as a larger sensitivity analysis. If we're in a sensitivity analysis, then we turn off plotting, we don't display the model time, and we put another flag here to turn on some other model features for the sensitivity. And then we fix our present day values within the model. So carbon cycle, sulfur cycle, phosphorus cycle. These are the size of the present day fluxes. For definitions of exactly what these fluxes mean, please see the published material. So for example, carb W is carbonate weathering, and these are typically all in moles per year at the present day. Some of these are calculated for steady state, and we have all the different cycles in the model represented here. We have a few of the key parameters: the oxic fraction of the ocean, present day concentrations of phosphorus and nitrogen, a few of the key things about the model that we load up at the start. We set the present day reservoir sizes. So all of this stuff is within the pars structure, that's the parameter structure. And these are the present day sizes of the reservoirs. So phosphorus, oxygen, atmosphere, ocean, carbon, crustal organic carbon, crustal carbonates, pyrite, gypsum, sulfate in the ocean, ocean calcium, nitrate, and strontium in the ocean and in the sediments. Once we've set all of our model parameters, we then load our model forcing functions. So these are the things that evolve over time. They typically represent tectonic and biotic changes as the model progresses over geological time. So we load a lot of forcings from the old COPS model. We load a few forcings here. BA and GA are basaltic and granitic areas, mostly used for strontium isotope ratios of weathering. You'll see some of these are .mat files, some of these are Excel spreadsheets, so you can save forcings as any kind of data file you like, as long as you read it in. We're then loading our degassing rate. We have some options on this forcing, so a mid, a max, and a min, which we can then look at in our sensitivity analysis. Once we've loaded our forcings, if we're within a sensitivity analysis, we generate some random numbers to test some of our sensitivity bounds. And then we begin initializing the solver. So we have a few things here. We choose when the model begins, when starts, when the model ends. So it's currently set up to run from 600 million years ago, minus 600 million, to the present day, 0. We then tell the model which timestamps it's going to print when it's finished. These are for the global climate maps. We set a few other parameters. An interesting one here is the maximum step. So the model uses an adaptive time step solver, OD15S. Now, if you set it to a very large maximum step, it will, so it's 1 million year steps. It won't always use this step. It will reduce when things are happening in the model. But if the model is moving very slowly, if reservoirs aren't changing, it will accelerate up to doing 1 million year steps. If you have short timescale effects in the model, then you may want to reduce this step size to make sure you don't miss them. So if you have a 10 or 100,000 year event in your model and it's going along at these maximum steps, it may miss the event. So you may want to reduce the maximum step size depending on what you're doing. Then we begin setting starting sizes for all of the reservoirs. So these are mostly set to their present day values, but sometimes they are set to non-present day values. Then we have an option to tune our initial parameters. So most of these starting reservoirs are their present day, so P0, Cal0, SR0 means a present day value. Some of these things we know weren't at their present day value at the start of the Phanerozoic, so particularly these large crustal reservoirs, G, C, Pyre and Gyp, Organic carbon in the crust, this is probably doubled or something like this over the Phanerozoic, so we wouldn't want to set this to 1. And what we can do is we can run a tuning algorithm on the model to decide these crustal reservoirs at the start. So here we have an output of a previous tuning round which guesses these parameter values for the start. So you can just leave it set up like this. You can manually alter this if you find the model isn't recovering present day sizes in the large crustal reservoirs. We then define the starting state. Largely here we let things begin at their present day value, but sometimes we don't. So we set the starting values up here and we just put them into the vector down here. And then finally we call the solver. So this is when we call ODE15S. We point it at the equations file. We tell it when to start, when to end. We tell it what the starting parameters are for the model and any options we want to include. The model then flips into the equations file and runs this. And when that's finished, we have a bit of post-processing. Now, I'll come back to this once we've gone through the equations file. So when the model is running, we first clear this dy array. So this is all the dy by dt's, everything that changes by time. We import the globals that we needed from the other script. And then we turn these numbers that the solver likes to use into letters that we can recognize. So the model likes to see Y1 as the phosphorus concentration in the ocean. We prefer to see that as P because we know what's going on if we do that. We then use geological time, so model counts in T, which is years. For a lot of things we want to do, it's easier to count in millions of years, so we make this conversion. We calculate the isotopic fractionation of our reservoirs by using a procedure dividing the reservoir size times its fractionation divided by the overall size. This will become apparent later on, so I'll show you those calculations. We then do a few basic parameter calculations here to work out how much CO2 is in the atmosphere in ppm, how much oxygen is in the atmosphere as a mixing ratio, and as a relative amount of oxygen, because everything the model does is in the terms of moles, and sometimes we need things in concentrations or ppms. We then look at the forcings for the current time step. So this part here interpolates all of the forcing grids to the current time. So forcing grids will typically be provided on perhaps a 1 million year timescale or maybe even more coarse. And this makes sure that whatever time point the model is in, it has a forcing for that time point. And there's a few options you can see here, setting forcings to 1 so they don't do anything, or setting them to numbers. Now I won't go through here what each of these forcings means. This is all in the literature, but this is the degassing rate. This is the weathering, biotic weathering rate. This is land plant evolution, carbon to phosphorus ratio in terrestrial material, burial depth of carbonates, basaltic, granitic area, pre-plant weathering, and then these are the fractionation factors associated with sulfate reduction and photosynthesis on land or in the ocean. We then have this sensitivity script that varies some of these forcings based on our random numbers if we're doing a sensitivity analysis. And then we move to the model calculations that occur every time step. Now the first thing we do in the model is we deal with the spatial fields, the keyframe stack. So this is something that the SCION model does, which is unique and different to predecessor models like COPS, which is where it uses this interpolation stack, which is our climate emulator, in order to fetch grids. So these are the two-dimensional grids for surface temperature, for runoff, that we can then use to calculate terrestrial weathering. So the first thing we do is we define a past and a future time, which is looking at our emulator and deciding where we are. So if the emulator has information for, say, 540 and 520 million years, and the model is at 530, we can choose those emulated periods either side. We calculate the distance to what we call the past and the future grid, and the contribution that they would have to our overall grid. We then look at the CO2 levels in the emulator and calculate where the model's CO2 is in comparison to the levels that we know about from the emulator. And we get a contribution from the upper and lower CO2 levels in the same way we get a contribution from the past and the future. We then use these contributions to calculate things like runoff, temperature, topography, land area, grid area, and topographic slope for both those past and those future time points at our interpolated CO2 level. And this means that the model has 2D fields to calculate things like weathering. So we then look at our runoff field, we look at our temperature field, we figure out our total erosion, which is based on runoff and topographic slope and temperature. We then use these weathering parameters from PMF's analysis. in order to use the West weathering equation and calculate total CO2 consumption from silicate weathering, which is what is here for the past and the future. We then calculate this all up and we total it up for the past and the future, look at those contributions, and we get an overall silicate weathering for the current model time point. Carbonate weathering currently follows a simpler approximation that is just based on the runoff at each different grid point, so it doesn't yet have an erosion dependence like silicate weathering does. We then take these grid interpolated variables and we get total silicate, total carbonate weathering. We also look at estimates of global average surface temperature taken from the climate grid and tropical temperatures and equatorial temperatures to compare to some of the proxy records. We also then look at where the model thinks the ice line should be, so we decide a critical temperature of -10 is where the continental ice sheets would be, and we ask the model to calculate where those should be in order, again, to match and compare to proxies. Once we've done this, we move to calculating global variables. So these are now things that are calculated as a single value for the entire model surface. So in this version of SCION, which is 1.1.6, we are still using a globalized temperature productivity metric for the land plants. This comes from the COPS model, so we have limitations based on CO2, based on O2, photorespiration, based on evolution, temperature, O2 and CO2. We get our mass of the terrestrial biosphere, and we have a fire function in here as well. We then have this F biota parameter, which looks at the land plant biotic weathering versus the pre-plant weathering, and then this multiplies by our silicate weathering to give us the overall global weathering, considering the biotic effects, which is here. Oxidative weathering follows the carbonate weathering, which is just runoff dependent at the moment, as does the pyrite weathering, except this also has a dependence on the amount of pyrite in the crust, and oxidative weathering has a dependence on oxygen and the amount of organic carbon in the crust. Gypsum weathering, again, just runoff dependent currently. Seafloor weathering is based on global surface temperature, so it's a marine process, so we just scale it with global surface temperature, and the degassing rate, sort of assumed to be related to the spreading rate. We then have our degassing rates, which use our degassing forcing, but also the composition of the crust. Burial of gypsum, burial of carbonates, weathering of phosphorus, which sums up the silicate, carbonate and oxidative components of total phosphorus delivery. Land phosphorus weathering, and then how much enters the ocean. We then figure out our P and N concentrations in the ocean. New production, carbonate burial in the ocean, carbonate burial on land. Pyrite burial, which is based on sulfate abundance, anoxia and carbon burial. Our marine anoxic fraction. And then we look at our nitrogen burial, our phosphorus burial in different phases, and then we calculate our nitrogen fixation and our denitrification. And then the final thing here is we have a reductant input of oxygen-consuming species from the mantle. So these are all the major fluxes in the model. Gone through this relatively quickly. You can find more information about this in the model publications. Some of these ultimately come from the geocarb models. Some of these were introduced in the COPS model. Now we have the reservoir calculations where we sum up the inputs and outputs for each of the major model reservoirs. So phosphate is in the ocean is the input, minus the 3 burial terms. Oxygen is the carbon burial, minus the carbon weathering, plus the pyrite burial, minus the pyrite weathering, minus our reductant, and so on and so forth. We then calculate our isotope reservoirs. So what we're doing with these calculations here is multiplying the overall flux by the isotopic composition of that flux. So it's sort of a weighted mean. By doing this, we get this parameter, which is delta org C times org C. This is a very convenient and easy thing to calculate, and it means that by taking this and dividing it by org C, we can come at the isotopic composition. So we found this to be a sort of numerically efficient way of calculating isotope compositions. We do this for atmospheric CO2, and we do this for marine sulfate, as well as the crustal reservoirs. Currently, the strontium system sits separate to the rest of the model because this was added at a later date. So we have all of our strontium fluxes defined here. We have our fractionation calculations here, and then we have the same things, our strontium concentration and isotopic composition in both the ocean and in the global sediments. We then do a few basic checks that the model is conserving mass, that it should be. And then the final action here is to record all of our states. So the MATLAB solver that we're using will record these dy variables, but it will not record all of the individual fluxes that go into it. So all of these things like basalt, granite, carbonate weathering will not be recorded by the MATLAB solver as a default. So what we do is we have this long list here of what we call the working state, which is for every model step number. Every time the model loops through at each time step, we record all of the things that we're interested in so we can look at them once the model's finished. Now, we also record the grid states. These are the 2D fields from the client model emulator. So we have the land, the runoff, the air temperature, topography, chemical weathering, carbonate weathering. So CW here is silicate weathering, carbonate weathering, and erosion. If we are doing a sensitivity analysis, we record a much reduced amount of states. This is so the model runs quickly when it's in sensitivity mode, and we just record the things that we're interested in outputting in our sensitivity analysis. We then finally make some outputs of the timestamp so we can see what's going on with the model while it's running. We iterate the step number so that these vectors can fill up properly. And then we have an option here to terminate the execution if the model is running for too long, which you can remove this if you want to do extremely long runs, but it just stops the model running aground. So once we've finished running the model, we would come out of the equations file, back to the initialize file, and we do a bit of post-processing. So we look at the size of the output, we say that we finished the integration. We then look at the shared values. So this is recording what the solver is outputting versus what we've recorded here in the working state. Because what this solver will do is it will take various steps that it then disposes of and doesn't use in its final calculation. So for example, it might take a long step forward, discover that the model has changed quite a lot, go back and use a shorter step instead. And the model will do this quite frequently. So if you look at your working state output, you will see that it takes often many more steps than actually recorded in the model output. So what we do here is we take all those final steps the solver was happy with, and we map the working state onto those to find out what we call the model state. So this is the final output of all the different model variables that are being calculated. We then save this as state, grid state, pars, params, and forcings, so we have everything we need to assess the output. We say that the model is done, and then we choose some plotting scripts to run, depending on what we've passed the model. So what I'll do now is an example run. Now, you should run the model initially for single runs by using the initialize file. So if I click run here, what I'm going to get now is an error because I haven't specified a run control. So if I've entered this into the console, for example, SCION initialize of nothing, it isn't going to work, so I have to enter one of these run controls. So if you go into the model guidebook and look, you'll find a list of run controls that you can do. The most popular is -1. So the ones that you should use are 0, -1, and -2. Now 0 gives you a full model output with all of the nice pictures. -1 gives you a simplified model output, so it doesn't run this big world graphic plotting script which shows you all the 2D climate fields. So those fields are generated and they are saved, but they're not plotted as a default. -2 will give you a present day spin up. So this is to be used if you're modifying the model or changing things and you want to make sure that it still spins up to the present day. So we'll begin by running 0. Now, instead of running it directly out of the console, it's best to name your run something. So I could call this run1 equals sign initialize of 0. This means that I have this run saved in the workspace, and I can go back and refer to it later, and I can save it. So we're setting parameters, loading forcings, and we're now going through the model. So what you'll see here is we've gone through the model steps, and this tells us roughly where we are in geological time, where the keyframe is. Now, you'll see here the reason we don't always want to plot all of these is because these large grid state plots can take a little while to assemble. So we're plotting here snapshots of the 2D model field over geological time in two different figures. So the second figure will show up at some point. So the information we have here is the continental distribution, which also includes an approximation of the topography and the ice cover at the top here. We have the global temperatures, surface air temperatures. We have the runoff, is on a log scale. We have the erosion rates, and we have the silicate weathering at the bottom. So you could choose different things to include here, but these are a generally useful subset. And you can see the ice expanding here. So of course this is all a prediction. we might have ice at times when there wasn't ice, and we might have no ice at the times when there should be ice. So you see in the model here, northern hemisphere glaciation happens too early. And this is because this is a predictive model that tries to predict from first principles how the world works, instead of really being told exactly what should happen. And this is kind of how the model is used as a research tool. So in addition to these model spatial outputs, we also get this summary picture of all of the fluxes. So this tells us the forcings, organic carbon, carbonates, sulfur species, carbon reservoirs, sulfur reservoirs, nutrients, F-org, fraction of carbon burial that is organic, fraction of sulfur burial that is pyrite. Then we have some proxy comparisons here. We've got 13C, 34S, 87, 86 strontium, marine sulfate concentration, atmospheric O2, CO2, global average surface temperature with the tropical temperature up here in red, and the model ice line compared to proxies. So there's a whole wealth of information that comes out of the model during the default run. Now, you don't have to save these figures because everything now is also included in this state. So if we have a little look in here, we have all of these state variables over time. So nitrate in the ocean, for example, in moles is here. We have our grid states. So these are 22 different time slices across the model run with things like air temperature topography that was plotted in that first script. We have the parameters we used for that model setup. We have sensitivity parameters, so we didn't use a sensitivity run here, so it's empty. And then we have our model forcings, so we can remember exactly what went into our model as the forcings. So that is one way to run a default run. What we can try to do now is we can look at run 2. If we just run -1, the model runs just as quickly, but we only output that first script. So this can be very useful, that first plot, sorry. This can be very useful for just making quick and simple model runs to test simple ideas. Finally, if we do a -2, this will now spin up the model towards a present day steady state. So it's using time 0 for the whole thing. It will still run the model for 600 million years, and it will still plot things against the proxies. But what you can see is everything is just very quickly coming towards steady state, towards the present day. So this is useful for setting up the model, making sure it's predicting the right sort of amount of CO2, the right O2, and various other things for the present day. So I'll leave that now for here.